All right, today we're going to look at solving nonlinear inequalities. Yesterday you had the opportunity to kind of refresh yourselves over the basic linear inequalities. Specifically, you looked at how to solve a linear inequality. Remember that when you multiply or divide by a negative, you have to flip the inequality symbol when solving. You also looked at how to graph a linear inequality. That's where you'll graph the line, determine if that line should be dotted or solid, depending upon what type of inequality symbol is in the problem, as well as test a point to figure out where to shade your solution set. Remember that inequalities have a range of solutions, not one specific value like an equation does. And then you also looked at compound inequalities that include both and or statements. Today we're going to kind of go further in depth with the solution set for an inequality. So again, the solution set represents all the solutions for that given inequality. There's 3 different ways that you're going to be responsible for being able to write a solution set for any given inequality. The first way to represent a solution set of an inequality is to use the real number line. In order to do this, you'll draw a number line in the horizontal direction, and any critical points that you put on the number line are either going to be filled in bubbles if they're included points in the solution set, or empty or open bubbles if those critical points are not included in the solution set. The second way to represent a solution set is to use what's called interval notation. And for most of us, this might be new. Interval notation simply means that I'm going to look at the intervals between each of the critical points on my real number line and dictate whether or not they satisfy the original inequality. Now, to do this, we're going to have to include these infinity symbols, both positive infinity and negative infinity. Those are going to represent the unbounded or limitless values in either direction of our number line. Because think about it, a number line goes on forever in both directions. To the left is for negative, to the right is for positive. So as we go further and further left, that's going to represent negative infinity. As I go further and further right, that's going to represent positive infinity. Since negative infinity and infinity are not considered real numbers because they're limitless, they go on forever, they are not specific numbers, and therefore they're just symbols. And so those values of negative infinity and infinity will always be excluded values represented by parentheses. If the solution set consists of several disconnected pieces, we're going to use this union symbol, capital letter U, to denote the different pieces or segments of the intervals that are included in our solution set. And then finally, the third way to represent a solution set is the one you're probably most familiar with, which is set notation, which uses the inequality symbols less than or equal to, greater than or equal to. Here are a few examples below of interval and set notation. So take a few minutes to go through each one of these and make sure you feel comfortable using both interval and set notations. All right, so here is the algebraic procedure for solving any nonlinear inequality. First step, always, is to use addition and subtraction to move all non-zero quantities to one side. So basically what I'm saying here is get everything to one side so that you have 0 on the other side of the inequality. If there are fractions involved, you're going to always want to simplify the side with the fractions into one single fractional expression. So if I have 2 fractions, whether I'm adding or subtracting those fractions, get a common denominator, reduce it down to a single fraction. That's step 1. Step 2, you're going to find your critical points, and those are the points that you're going to list on your number line. Your critical points include both the solutions as well as any excluded values. Now, we talked about what an excluded value is. An excluded value is a value that makes the expression undefined. To help you with this, you're going to have to remember your factoring skills. There's 3 different types of functions that I'm going to throw at you guys during this nonlinear inequality unit. Polynomials, rationals, and radicals. With polynomials, whether it's a quadratic, a cubic, a 4th degree polynomial, those will never have any excluded values. So once you solve that polynomial equation, those are your critical points. With rational inequalities, remember rational means a fraction. And we know that when I have a denominator of 0 in a fraction, it makes the fraction undefined. So any excluded values are going to exist where the value makes the denominator 0. Those have to be included as part of our critical points listed on our number line. And with radical inequalities, remember, we're dealing with a real number line. So any values that make the radical imaginary are the ones that make the radical negative inside. Those values are also going to be included as part of our critical points found on our number line. Now in step 3, we're going to determine whether or not those critical points are part of our solution set for our given inequality. To do this, we're going to make a sign chart. And what that sign chart is going to do for us is it's going to tell us whether or not that particular interval is included or not included in our final solution set of our original inequality. And then in step 4, once we have our selected intervals that satisfy our original inequality, we'll go ahead and write that solution set using either set notation or interval notation or even both. Let's look at example 1. It says solve each inequality, state the solution set 3 ways. So I'm asking you to write it as a number line using interval notation as well as set notation. So the first 2 examples deal with polynomial inequalities. These are our quadratics, our cubics, our 4th degree polynomials. So in example 1, I have a cubic inequality that's already been factored. So everything's moved to one side. I'm going to rewrite this as an equation with the given factors of x plus 3 times x minus 4 times x minus 1 equals 0. To solve for my solutions, I'm going to set those factors equal to 0, and I get x equals negative 3, x equals 4, x equals 1. Since this was a polynomial inequality, remember there are no excluded values. So these are my 3 critical points, and I'm going to write them in numerical order from left to right. So negative 3, 1, 4. And now you can see here I have a bunch of different intervals. This first interval all the way on the left is from negative infinity to negative 3. Then I have the interval from negative 3 to 1, then 1 to 4, and then 4 to positive infinity. So when we look at this number line, we always go left to right, and in this case I have 4 intervals, 1, 2, 3, 4. Now, to figure out if these critical points are included in our solution set, we have to look at our original inequality statement. We had a less than or equal to symbol, and we learned yesterday in the prereq work that these are included values. They are included in our solution set. Now, to figure out which intervals are included in this given inequality, we're going to have to make our sign chart, which is step 3. So I'm going to start all the way on the left with this first interval from negative infinity to negative 3. To test whether or not this is a part of my solution set, I'm going to pick a point within this interval. So something between negative 3 and negative infinity would be negative 4. So I'm going to plug negative 4 into this original inequality. Negative 4 plus 3 times negative 4 minus 4 times negative 4 minus 1 has to be less than or equal to 0. And if you do the math, that is true. Now let's pick a point in between the interval of negative 3 and 1. Maybe I pick 0. 0 plus 3 times 0 minus 4 times 0 minus 1 has to again be less than or equal to 0. And if I plug in 0 into that, I see that it is false. It does not satisfy that inequality. Now I got to test the point between the interval of 1 to 4. Let's pick 2. So I got 2 plus 3 times 2 minus 4 times 2 minus 1 has to be less than or equal to 0. And that is true. And then finally, for my last interval, 4 to infinity, I need to pick a point in between that interval. So maybe I pick 5. 5 plus 3 times 5 minus 4 times 5 minus 1 has to be less than or equal to 0, and that is false. So we just established which part of the intervals on our number line are included in our solution set. We have from negative infinity to negative 3, and then we also have from 1 to 4. So this would be my solution set represented by a number line. Now I need to write it in interval notation. And interval notation, remember, is the one where we use the parentheses and brackets. So for interval notation, it's negative infinity. That always gets a parenthesis to -3. -3 was included, so I'll give it a bracket. Then we have a jump to 1 to for the next interval, 1 to 4. So I'm going to put union, and then 1 is included, so it gets a bracket, 4 gets a bracket. And that would be my interval notation. Set notation would be x is less than or equal to -3, or x is greater than or equal to 1 and less than or equal to 4. So that would be my solution set, writing it both as an interval notation and as in set notation. All right, example 2, we have a 4th degree polynomial. This time it's x to the 4th minus x cubed minus 12x squared is less than 0. Everything's to one side. I'm going to go ahead and make this an equation. I can factor out an x squared. I can factor this trinomial inside the parentheses in the x minus 4, x plus 3. Set these factors equal to 0. I get 0, 4, -3. So these are my critical points because it's a polynomial and we have no other excluded values. So I have -3, 0, 4. And then I can go ahead and test points between each of these 4 intervals to see whether or not it's included in my original inequality. So if I pick a point to the left of -3, let's say I pick -4 again, if I plug it into the original inequality, I would see that this is going to be false. If I pick a point between -3 and 0 in that interval, let's say I pick -1, I would see that it satisfies the inequality, so true. If I pick a point between the interval of 0 to 4, let's say I pick 2, if I plug 2 for x into that original inequality, I would see that I get a true statement. And then if I pick a point to the right of 4 and plug it in, I would see it's going to be false. It does not satisfy that original inequality. Now, looking at our original inequality, it's less than. So these critical points are going to have open circles. And I need to shade in the values that were true. So the interval from -3 to 0, as well as from 0 to 4. So this would be my answer, represented by the number line. Interval notation would be -3 to 0. Again, those are not included, so they get parentheses. Union 0 to 4. Now, if you're wondering why I couldn't write it as -3 to 4, that's because 0 was not included, so I have to indicate that in my solution set. And then set notation would be x is greater than -3 and less than 0, or x is greater than 0 and less than 4. So that would be the 3 ways that I could represent my solution set for example 2. So as we turn our attention to rational inequalities, we're now dealing with fractions, which will have excluded values. Those are the values that make the denominator undefined, which would be the value that makes the denominator 0. So to get started with, I'm going to write this equation. X minus 1 over x minus 4 is equal to -2. And -2 I can write as a fraction. It's just -2 over 1. And now to solve this proportion, remember you cross multiply, which means I multiply my diagonals and set them equal to each other. So if x minus 1 times 1 equals -2 times x minus 4. So I get x minus 1 equals -2x plus 8. Bring the 2x over, that would become 3x. Bring the 1 over, that's 9. I get x equals 3. Now, if you look at, this is my solution. However, there are excluded values that make the denominator 0, which would be undefined. So what value makes the denominator 0 is if x is 4, since 4 minus 4 is 0. So there's my 2 critical points, 3 and 4. So this time I have 3 intervals, negative infinity to 3, 3 to 4, 4 all the way to positive infinity. So I got to go ahead and test points in each interval to see which parts are going to be part of my solution set. So if I pick a point to the left of 3, let's say I pick 2, and I plug 2 into the original inequality, I get 2 minus 1 over 2 minus 4 has to be greater than negative 2. Well, 2 minus 1 is 1, 2 minus 4 is negative 2, has to be greater than negative 2. Negative 1/2 is greater than negative 2, so that's true. If I test a point between 3 and 4, maybe I pick 3.5. If I plug it in, I'll see it's false. And then if I pick a point to the right of 4, let's say 5, I would see it's true. Now, I forgot to indicate whether these critical points are included or not. 3 was a solution. However, the inequality was greater than, so it gets an open symbol. And since 4 was an excluded value, that's always going to get an open circle, because if we included it, it would make the original inequality undefined. So the intervals that are part of our solution set are from negative infinity to 3, as well as 4 to infinity. So this would be my solution set represented by a number line. And then in terms of interval notation, we would have negative infinity to negative 3, union 4 to infinity. Set notation would be x is less than negative 3, or x is greater than 4. All right, looking at number 4, we have 2 over x plus 3 is less than or equal to 4 over x minus 1. I'll make this an equation. We need to cross multiply. So I have 2x minus 2, if I distribute, equals 4x plus 12. Solve for x, I get 2x equals negative 14, or x is equal to negative 7. So that is my solution. And then there are 2 excluded values. X cannot equal negative 3, and x cannot equal 1. So we have negative 7, negative 3, 1. You can even write excluded value for these two to remind yourself that these are always going to be open. And for negative 7, that was a solution, and the inequality is included. So now I got to test points to figure out if it's true or false. And we would get, let's see here, false, true, false, true. So our intervals that are included in this given inequality are from negative 7 to negative 3 and 1 to infinity. So that would be my solution set represented by the number line. Interval notation would be negative 7 included to negative 3 not included, union 1 not included, to infinity not included. And then set notation would be x is greater than or equal to negative 7, less than negative 3, or x is greater than 1. So there would be my 2 other notations. All right, last example, example 5, we're dealing with radical inequalities. So remember, with a radical inequality, we need to find excluded values that make the inside of the radical negative, because that would lead to an imaginary solution, which is not included on the real number line. So first step, we're going to write this equation as 8 minus the square root of 3x plus 4 equals 3. I need to subtract 8 from both sides. Negative square root of 3x plus 4 equals negative 5. Get rid of the negative by dividing both sides by negative 1. 3x plus 4 equals 5. Square both sides. 3x plus 4 equals 25. 3x equals 21. X has to be 7. So now we got to figure out what value needs to be excluded because it makes the inside of the radical negative. So I'm going to take the radicand 3x plus 4, and you're going to simply make it greater than or equal to 0, right? As long as it's 0 or higher, that will be fine because it will still lead to a positive solution. But anything that makes it negative will lead to an imaginary solution. So 3x is greater than or equal to negative 4, divide by 3. X has to be greater than or equal to negative 4/3. So these are my critical points. Negative 4/3 and 7. Now we got to determine whether these critical points are included in our solution set. So when x is negative 4/3, that was included, and x is 7, you got to look at your original inequality, that was also included. Now we know that any point to the left of negative 4/3 isn't going to work because if I plug it in, I'm going to get an imaginary solution, so that's false. If I test a point between negative 4/3 and 7, I would see that the original inequality comes out to be true. And if I pick a value to the right of 7 for my last interval, I would see again it's false for the original inequality. So my solution set is from negative 4/3 to 7. In terms of interval notation, that would be negative 4/3, comma 7. Both are included. And then set notation would be x is greater than or equal to negative 4/3 and less than or equal to 7. So those are my 3 ways to represent this radical inequalities solution set.